Okay, so we'll continue with our continuum treatment of phase separation. What we saw in the last segment was how the presence of this chemical spinodal in the free energy curve with respect to concentration introduces the physics of phase separation. Okay, and the crucial picture that we have to have is the following, right? The plot of free energy right? So when it has that non-convex shape, phase separation happens. Okay, C alpha, C beta, okay, and we saw that this is the chemical spinodal, right? The region where the free energy is non-convex. All right. And we saw by looking at those, all right, I demonstrated in 1D how this happens. We looked at what the presence of this chemical spinodal does for our equation for mass flux, right? Our constitutive relation for mass flux, how it causes uphill diffusion, right, or uphill transport, sorry. And okay, and we saw also that if we look at a continuum body, right, omega, we saw that what tends to happen is that the material phase separates, right? So let me draw those regions, right? So what tends to happen is that it separates into these phases. Okay. Now, just for the purpose of argument, let's suppose that these green colored regions are the phase beta. Okay, and the region around it is the other phase alpha. Okay, so around it is alpha. Okay, now one thing that the formulation as we've described so far does not do is the following. We know that it gives us the phase fractions, right? It gives us the fact that VB, V beta, is equal to the following, right? V beta we said is equal to C minus C alpha divided by C beta minus C alpha times the total volume of the mixture, all right? And V alpha, which is the total amount of alpha, right, is C beta minus C divided by C beta minus C alpha times V, okay? And in this, C is the average concentration. Okay? All right. What the formulation so far does not explain for us is the question of, well, okay, if we know that this is the total volume of V beta and this is the total volume of V alpha, what we mean is that V beta is got from all these guys, right? All these little particles together contribute to V beta. this one as well. They all give us V beta. So what the formulation does not tell us as well is that how things look, or do they look this is our body, omega. Is that how things look, or do the particles form of bigger size but fewer in number, right? So do we have something like that, or do we have maybe just a couple of large beta particles? Okay, right, where the rest of it is alpha. Okay, so do we have these two particles together giving us the same volume V beta as we have above? Okay, which of them is right? Is it this one or that one? The formulation does not tell us that. And it does not tell us that because there is something critical missing in this formulation. If you have a background in material science, or you've considered related problems, you may have an idea. So think about it. There is something about these two pictures, which I've just drawn, which the formulation does not address at all. It does address the total volume of beta. It does address the total volume of alpha. But it does not address something else which controls the way in which beta and alpha distribute themselves into certain numbers of particles. What it doesn't tell us is how big those boundaries between alpha and beta are. Okay? All right. So let me tell you first, write down what the formulation does not give us. The formulation described thus far does not address the size and number of beta phase particles making up the total volume V beta. And of course, if it doesn't tell us about V beta, it obviously doesn't tell us about V alpha either, right? Okay. Similarly for V alpha. So, have you been able to come up with what is missing in the formulation? What is missing is something we haven't spoken about in this class, and that's why I said you may know it from other sources. It hasn't said anything about this concept called an interfacial free energy. Okay? So let me put that down. The interfacial free energy is missing. Okay? And here's what we mean. If we have a body, omega, and of course the basis is always there, right? Right, we have this body, omega, and we have these particles. Okay. Now, what this formulation does tell us is what the free energy of the system is in each of these phases, right? So it does tell us that here, okay, the total free energy that's contained in those two phases, okay, in those two volumes, is V beta, the volume, times chi evaluated at C beta. Okay, because chi as a function of C beta is a free energy per unit volume times the volume of the total volume of beta gives us a total free energy. Okay. Okay. That's the free energy which comes from this notion of a free energy per unit volume, which is chi. Okay. Okay. And likewise, since these regions are alpha outside, we know that the free energy coming from there is V alpha times chi evaluated at C alpha. What is missing is the idea of an interfacial free energy which arises every time you have an interface between alpha and beta. Okay? And the fact is that the physics tells us that, and chemistry also tells us, that every time you have an interface between materials, there is a certain free energy associated just with that interface. Okay, so in a 3D setting, there's a certain free energy associated with the surface, that interfacial surface between alpha and beta. Okay, so there is an interfacial free energy, which I am going to denote by uppercase gamma. Okay, so gamma is a free energy per unit area of interface between alpha and beta. The reason it exists is because across this interface between alpha and beta, across this interface between alpha and beta, the chemistry of the material is changing. Okay? Right? Across this interface between alpha and beta, if you go out in that direction, what you will see is that the chemistry is changing from beta to alpha. Okay? So the chemistry changes normal to the interface. Okay, and what I'm going to do is I'm going to denote that interface as S. Okay. The reason the chemistry changes is because the nature of bonding is changing as you go from beta to alpha, or as you come from alpha to beta. Okay. So the nature of chemical bonding changes across S. Okay, as you go from alpha to beta. across, so it changes across S from alpha to beta, or obviously, or the other way around. Okay? What happens with the chemical bonding is that the way in which bonds are formed, what is bonded to what, changes as you grow across beta to alpha. Because if you're entirely within beta, every material, around every bond is more beta, right? Around every atom or molecule is more beta. If you're in alpha, well, around every molecule is more alpha. Across the interface, that is changing. Okay, and because of that, as the bonding structure changes, there is a certain amount of energy associated with the fact that that bonding is changing. Often it happens that there are some bonds which are just left unsatisfied across an interface. Okay, and the energy of those bonds remains high if they're unsatisfied, and so that manifests itself as a free energy. Okay, and interfacial free energy. So it's important that in general it is because the nature of the chemical bonding changes. Okay, this is where it comes from. Okay, how can we represent it? Think about it. I'm going to write something here to help you think about it. Within alpha, the concentration is pretty much C alpha. Within beta, the concentration is pretty much C beta. We know that C alpha is really quite different from C beta. Okay? As we go across that interface, we are going to see a significant concentration gradient. Okay? And that concentration gradient manifests itself in this nature of bonding changing. Okay? So, the simplest way in which to represent a free energy here, an interfacial free energy, is to say that that gamma depends upon grad C. Now it's an energy, and we want it to be positive. Okay? So the way this is done is to simply write out a quadratic function of the gradient of concentration in that fashion. Okay? Where K is a positive, definite tensor. Okay? Because K is positive definite, it implies that gamma is greater than 0 if there is a concentration gradient. If the concentration gradient is non-zero, right, anytime the concentration changes between alpha and beta, or anytime there's a significant concentration gradient, there is and effectively there's an interface there, okay, and because the nature of bonding can change, the material says that, the physics tells us that energy must be stored there at that interface. Okay? All right. This is the way in which we represent the interfacial energy, and okay, what I'm going to do here is actually to do the following. Now, the way I've defined gamma up here is to say that there's a free energy per unit area of interface. Okay? But what this type of a formulation allows us is the idea that the interface, that you can sort of smear out this interface. Okay? So rather than represent it actually as a free energy per unit area, I put a gamma sub V there to say that this effect of having a surface, an actual mathematically sharp surface, can be represented if instead of actually having a surface, we have a region where the concentration changes from alpha to beta. Okay, so here's what happens. So we have finally this thing again is a free energy per unit volume. Okay, and the way it is related to gamma, which I introduced up here, is the following. Okay, so if you have a region omega with a beta particle inside it, right, that is the interface S, and let us suppose that area of the interface S is A sub S. Okay, all right. Instead of representing it that way with a sharply defined surface, this formulation that we are recommending based on concentration gradients does the following. Takes the body, okay, and what it does is to it does the following. It smears out that area here's what I'm going to do. It smears out that area into a sort of band where things change from alpha to beta gradually. Okay, and to represent that band, I'm going to put in some other color between red and green. I'm going to say yellow. Okay, hopefully you will be able to see this. I think you can. Okay. All right, so that sort of contour of those contours that I've drawn going from red to yellow to green is a sort of smeared out interface of some finite width across which the concentration is changing from alpha to beta, from C alpha to C beta. Okay, so inside here the concentration is C beta. Outside of it, it is C alpha. Well outside of it, it is C alpha. Okay, and as we go across that interface of some thickness, okay, the concentration is changing. Okay, that's where we pick up a concentration gradient. All right. So what this is doing is it has replaced the area, okay, with some region of finite width. Okay, so what is done here is that we say that the interface S is replaced with a smeared out region of finite width across which gradient of C, the normal or the norm of gradient C, the Euclidean norm of gradient C is less than infinity. Okay, so we get some finite gradient. On the other hand, in this sort of a picture, if things change from C alpha to C beta suddenly, there would be a discontinuity in concentration, right? And between alpha and beta, there would be a discontinuity in concentration across that sharp surface. And we would pick up, in this case, we would pick up gradient C, the norm of gradient C is unbounded. Okay, so what is the overall effect here? The overall effect is that whereas in this case the effective free energy of that interface would be the total free energy in the case with a sharp interface would be integral of gamma dA over that interface. In this case, the free energy of the smeared out interface is integral over the whole body, okay, of gamma V dV, okay, right. To be consistent with the way I'm writing things, I should write that A as a little a. Okay, all right. Getting back to, all right, so getting back to this. The free energy in this case is integral gamma V dV, where gamma V now is half gradient of C dotted with this positive definite tensor, gradient of C dV. Okay, so we're representing it in this fashion. Okay, all right. Well, this is how we're going to write things out. We're going to stop the segment here. When we come back, we will go back to our mass transport formulation and work out the mathematics with this representation of the interfacial free energy.